All right, so it'd be a good idea to take a moment and read through problem number, 99. We've already done 98. Whew. All right, so what's interesting about 99 is, well, first of all, the same question is being asked. Find the total distance traveled by a particle whose velocity is represented by this equation. Okay, so find the total distance traveled, got it. One less thing for us to do is find the derivative of a position because it flat out gave us the velocity. So what we're going to do is we're going to find the total distance on the time interval from 1 to 4. It tells us that in the problem. So the setup of the absolute value would look something like this. And if we did have a calculator, Y1, you'd want to type in the absolute value of this expression. Go to the home screen and using the necessary keystrokes, evaluate the integral, and you would have the total distance traveled. Without a calculator, how do we kind of proceed with this? Well, again, we would need to know where this velocity graph is positive and where it's negative. So I'm not familiar with how to graph this as far as factoring. Okay, so we might just want to use our mental math to help us get a sketch of this graph. So we're trying to take a peek into the velocity graph to see if it ever becomes negative, to see if we need multiple integrals to represent the total distance traveled. Okay, well, I can see that I'm restricting my look at time values from 1 to 4. So here's 1 and here's 4. And so if we think about just plugging in time values here, if time is 1, if t is 1, then the velocity is 1. All right, easy enough. If I were to evaluate at 4, then I can see that that would be 1 over square root of 4, or 1 over 2, so that'd be 1/2. So it appears that if we reason through this, that as time increases, if the value of this gets larger and larger, then the square root down here would also become larger than the previous value, so that the value of the whole fraction is decreasing. Now, the denominator is getting bigger, so the value of the fraction is going to 0. So it looks like we have an asymptote. Okay, so I really don't care about what's happening between time equals 0 and 1 because we're told to only look at this graph from 1 to 4, but I think it's worth noting that if you get closer and closer to 0, if time is 0, this function is undefined. We have a vertical asymptote. So the y-axis becomes a vertical asymptote, which tells me that as I travel back to the left from time equals 1, that I bet the graph is increasing without bound like this. Okay, and if you're interested, you might want to take this velocity equation, type it into y1, and see if you set a good window that you get this graph right here. All right, so easy enough. Our velocity will never be negative, and think about that because these are all positive values between 1 and 4, and our denominator will always be positive, so our answer, our velocity values will always be positive. So actually, we don't need multiple integrals, we just need one. And that's it, and the absolute value is not necessary. So we're looking for this amount of accumulated space, which represents the total steps traveled to the right by this particle. So really, over here, I'm going to release the absolute value. I don't need it. I'm going to go ahead and insert the equation for velocity and rewrite it as t to the negative 1 dt. So this one's easy enough to calculate. We'll go ahead and finish this one. So let's find the antiderivative. Increase the exponent to a half, divide by half, but that's multiplying by 2. Evaluate from 1 to 4. And I'll come down here and do that. Alright, so what's the y value on the antiderivative at 4 and the y value at 1 on the antiderivative, and the difference of the two, because that equals this accumulated change. Twice square root of 4 minus twice square root of 1. You could also factor out the 2 or not bother with the 2 here, factor it out and just evaluate the antiderivative part of t to the 1/2 at 4 and 1. I'm just saying you could pull out a 2 in the very beginning here, and it kind of makes the numbers easier to work with. So what is this, 4 minus 2? So 2 units. Okay, I strongly encourage you to read through problem 100. It's an interesting problem about statistics, actually probability. And you're given an integral that represents a probability that a needle will touch a line. So, but the final question is find this probability. So that just relates to us finding the value of this integral. Notice that there's a constant multiplier, so that's a little bit different in the previous problems that we've seen. There's a constant multiplier 2 over pi out front here. All right, so without a calculator, let's find the value of this integral and multiply it by 2 over pi. It looks like the integrand is ready for integration. So if you wanted to, you could bring in a sign or a negative here and pull a negative out here. If you bring a negative in, you got to pull a negative out here to undo that. And the reason I did that is because I know that the derivative of cosine is negative sine. So integrating, I'm going to get cosine of theta, and I'm going to evaluate it from 0 to pi over 2. So I'm going to use my bracket as my evaluation bar. It's just kind of a nice convenient thing to use there. Okay, and here I'm just going to leave the negative 2 over pi out in front. I could have done that up here too with that constant multiplier, but it's convenient to do so here. So negative 2 over pi. Okay, so just cosine of pi over 2 minus cosine of 0. All right, cosine of pi over 2 is 0 minus cosine of 0 is 1. All right, so the result will be negative 1 times negative 2 over pi, or just simply 2 over pi. Okay, the interesting part of problem 100 is perhaps just that we're returning to trig integrand and working with that there. So tried to look at 4 different examples of problem situations in which the fundamental theorem of calculus can be used to help us solve those problem situations.